Imagine a lonely world drifting through the infinite dark of the Milky Way. It has no sunrise, no parent star, no orbit to mark the passage of years. These rogue planets, or free-floating planetary mass objects, are some of the most mysterious entities in our galaxy. Science has often defined planets as companions held by a star's gravity, bound in a celestial clockwork. Yet, nature does not ask our permission to create wanderers. Out there, in the vast lanes between stellar neighborhoods, billions of these objects may exist, cold and dim, moving like stones in a slow, invisible river. Why do they wander? Is it possible that the galaxy is not just a collection of star systems, but a crowded gathering of abandoned worlds? We are beginning to uncover a history written in velocity and gravity, a story of worlds that lost their light or perhaps never knew a sun at all. The silence of these rogue worlds is not emptiness, it is a profound scientific riddle waiting to be solved by those who know how to read the fingerprints they leave in the starlight. Most rogue planets are the result of violent cosmic instability. In the crowded nurseries where stars form, planetary systems are born in a state of chaotic flux. Giant planets, in their migration and gravitational interactions, act as bouncers at a cosmic dance. When two massive worlds get too close, they trade orbital energy in a way that fate often dictates for the smaller partner. The unlucky planet is flung outward, crossing the escape threshold to become a traveler of the galaxy. This ejection is not a sudden explosion but a mechanical consequence of gravity. A planet that once belonged to a neat family portrait suddenly finds itself released from the central pull. We see this process in our own solar system models, where giant gas giants may have rearranged their positions, potentially ejecting smaller icy bodies into the dark. These are not rogue villains, but survivors of a gravitational argument that they simply could not win. They carry the chemistry of their birth system, a memory of a star that faded behind them long ago, now just a distant point in their black sky. However, there is an entirely different path to loneliness that suggests these worlds were never part of a star's family in the first place. Some rogue planets are likely born alone, condensing directly from small collapsing fragments of cold interstellar gas and dust. In the deep, dark molecular clouds where stars begin, gravity occasionally gathers just enough material to form a round, planetary mass object without reaching the temperatures required for nuclear fusion. These failed stars never glowed, they were born in the shadow of the nursery, small and dim from the very beginning. By some definitions, they are sub-brown dwarfs or isolated planetary mass objects, blurring the line between a planet and a star. Nature smudges the categories we so carefully label. If an object is massive enough to have an atmosphere, internal heat, and a core, does it matter if it formed in a disk or from a cold clump of gas? These born-alone wanderers suggest that star formation itself is a spectrum, reaching down into planetary masses, creating orphans that never had a parent to leave. The reality of rogue planets is likely a complex combination of both mechanisms, creating a vast, diverse population across the Milky Way. We are discovering that these wanderers represent a wide spectrum of histories, compositions, and origins. Some are indeed exiles from chaotic systems, carrying scars from ancient gravitational encounters, while others are the cold, isolated embers of star formation that never quite ignited. The Milky Way might not just be a galaxy of stars with planets attached, but a galaxy of planets that have slipped their leashes or never wore one at all. Future surveys, utilizing advanced methods like gravitational microlensing and the infrared sensitivity of the James Webb Space Telescope, are finally allowing us to build a census. We are moving from identifying single, mysterious wanderers to recognizing them as a major component of the galactic population. Whether they carry hidden subsurface oceans warmed by internal heat or remain frozen shells of gas and rock, they occupy a borderland where physics tests our definitions of what it truly means to be a world. The existence of rogue planets compels us to rethink our place in the cosmos. We live on a world connected to its star, where light dictates our sense of time, rhythm, and life. To imagine a world without a sunrise is to face the fundamental indifference of the universe to our need for a center. Yet, these wanderers are not outside the laws of nature, they are deeply connected to the galaxy by the same gravity that holds the stars in their spiral arms. Every atom in a rogue planet was forged in the hearts of ancient, exploding suns. They remain part of the cosmic fabric, drifting through the dark with their own secrets. maybe the true lesson of these solitary travelers is that the universe is far more inventive than our early diagrams suggested. The dark between the stars is not a void, it is a place filled with slow, quiet histories, where heat hides beneath ice and gravity guides movement over billions of years. When we look at the sky tonight, we should remember that the light we see is only half the story. There are countless worlds moving through the night, silently, patiently, waiting for us to notice the ripples they leave in the fabric of the dark. There is a silent, invisible cage surrounding every observer in the cosmos. It is not built from solid walls or dark matter, but from the fundamental velocity of light and the finite age of reality itself. We reside within a bubble of information, a slice of the universe centered on our position, constrained by the simple fact that light takes time to travel. Every star you see at night is not a current representation of that object, but a delayed message from its past, delivered with the punctuality of a signal that had no other choice but to move through the void. The speed of light, constant at nearly 300,000 kilometers per second, defines the absolute boundary of our cosmic window. This is the observable universe, a sphere defined not by space, but by time. We are essentially trapped in an archive of different eras, where time is folded and flattened into a single static projection on our night sky. What remains beyond this horizon is permanently inaccessible, existing in a state of causal isolation that physics describes with cold precision. You are looking at multiple pasts at the same time, unaware that the present of these distant reaches is permanently beyond your grasp. The universe as we measure it appears as an absolute, fixed sphere defined by the maximum distance light could have traveled since the Big Bang. If the cosmos has an age of approximately 13.8 billion years, then light from the furthest reaches has had exactly that amount of time to reach our detectors. This creates a hard physical limit, a boundary inscribed in the very fabric of space-time. Within this sphere, gravity and electromagnetic forces have governed the evolution of matter, allowing for the formation of galaxies and the synthesis of elements. We define this region as the observable universe, the totality of what history has allowed us to connect with. It represents a volume of reality containing trillions of galaxies, each housing hundreds of billions of stars, and presumably, countless planetary systems. This is the standard portrait of our existence, a sphere of influence where causal connections are possible, and where light remains the ultimate mediator of reality. Every atom of your body, and every photon that strikes your eyes, is derived from processes occurring within this singular, finite bubble. Our understanding of the laws of physics is built upon the interactions contained strictly within this specific, ancient, and well-mapped light cone. However, the universe is not a static container, and the space between galaxies is not merely a distance to be traversed. Space itself is expanding, a dynamic process that fundamentally alters the nature of our cosmic bubble. Hubble demonstrated that galaxies are not moving through space, but rather that space itself is stretching, carrying them away from one another. This expansion means that the region which emitted light 13.8 billion years ago is no longer at the distance it occupied when that light began its journey. Our observable universe is actually 93 billion light-years in diameter, not 13.8 billion, because space has continued to expand throughout the transit of the photons. This is a universe in constant motion, a dynamic system where the local geography is being rewritten every second. Moreover, the discovery of dark energy has revealed that this expansion is not slowing down under the pull of gravity, but accelerating. This acceleration pushes the horizon further away, creating a cosmological event horizon. What was once distant and eventually accessible now threatens to vanish entirely as the bridge between us and those regions grows faster than light can cross it. We are not static inhabitants of a fixed sphere, we are living on a rapidly dilating rubber surface where distant points recede into an eternal, unobservable silence. Our cosmic horizon is therefore a frontier that paradoxically isolates us as it expands. While the sphere of information grows in volume, the number of distinct sources we can realistically influence or observe in their current state is diminishing. Accelerated expansion functions like a slow evaporation of the cosmic lake, where galaxies are pushed beyond our cosmological event horizon one by one. This transition creates a deep asymmetry. We see the ancient past of these regions, but their present-day states are severed from our causal history forever. We live in a brief, privileged moment of cosmic time where the light of distant structures is still reaching us before they fade into the redshifted abyss. As we observe the sky, we are essentially witnessing a fading archive, an archive that will be significantly more empty for observers billions of years from now. This synthesis reveals that the observable universe is not a permanent room, but a narrowing window. We are situated observers in a cosmos that is structurally designed to gradually prune away its own history from our view. The more we learn about the acceleration of the void, the more we recognize that our visibility is tied to a clock that favors isolation over connection. To exist within this boundary is to recognize that we are a species living within a structural limitation of reality. There is reality beyond the horizon, a reality that is physically continuous and governed by the same laws, but it is effectively and permanently non-existent for our instruments and our causal history. The total universe is likely vast, perhaps infinite, and our observable bubble is merely a local fragment, a tiny, privileged sample of a much greater whole. This does not diminish the value of our cosmic exploration, but rather highlights the importance of the brief interval in which we can study the stars. We have managed to map the structure of our existence, to identify the laws of gravity and light, and to name the forces that drive the expansion of space. We are the mechanism by which the cosmos describes its own limits. By observing the horizon, we are defining the contours of the knowable, acknowledging that even if there are infinite versions of reality beyond our reach, our local story is the only one we can verify. The night sky is a silent confirmation that reality does not require an audience to be real. As we look into the dark, we accept that the horizon is not a failure of our technology, but a fundamental property of an expanding existence that reveals itself only in small, precious, and fleeting doses. What happens if we travel back in time, stripping away the layers of cosmic history until we reach the very threshold of existence? We imagine the universe as an expanding film, and if we rewind the reel, everything shrinks back to a singular, dense point of infinite heat. It is a compelling mental image that sits at the foundation of modern cosmology. We are conditioned to seek a beginning, a moment of birth that defines our reality. Yet, this search for an origin point may be a fundamental misunderstanding of the physics at play. The concept of a definite start implies a preceding time, a moment when the clock began ticking. But what if the very concept of before loses all meaning in the face of the extreme conditions governing our universe? We are standing on the edge of the ultimate mystery, looking into a void that defies our most basic grasp of chronology. Prepare yourself to challenge the logic of time itself, for we are about to look beyond the edge of existence. The traditional Big Bang model posits that our universe emerged from a state of infinite density and heat 13.8 billion years ago. Within this framework, space and time are inextricably linked. If we accept this singularity as the absolute origin of all matter and energy, then the question of what happened before is empty. Time, by definition, began when the universe expanded. To ask what occurred prior to that instant is like asking what lies north of the North Pole. It is a linguistic construction that lacks a physical referent because there was no time in which an event could have unfolded. The singularity marks the definitive start of the space-time continuum. Everything we observe, every galaxy currently moving through the observable universe, and every law of physics traces its pedigree to this single, explosive initiation. We must accept that time is a property of the universe, not a stage upon which the universe appeared, rendering the search for an antecedent cause logically impossible within our scientific framework. Physics, however, rarely allows for such absolute terminations without inviting skepticism. Alternative models propose that the Big Bang was not an act of creation from nothing, but a dramatic transition from a pre-existing state. Consider the idea that our universe is merely a single phase in a much larger, infinite cycle of contraction and expansion. In this view, density increases until the fabric of reality reaches a state of total collapse, only to bounce back in a new epoch. Here, the universe possesses a history that stretches back through an infinite sequence of prior states. Time did not start at the Big Bang, it simply changed its characteristics. The laws of nature might operate in a fundamentally different way in these earlier epochs, with time acting as a dimension that mirrors the properties of space. This perspective denies the singularity as an origin and instead frames it as a cosmic gate, a gateway between one manifestation of reality and the next. This challenges the notion of a unique beginning, suggesting that what we perceive as the dawn of time is merely the horizon of our current observational reach. Stephen Hawking proposed a revolutionary synthesis to resolve this impasse known as the no-boundary proposal. By applying quantum mechanics to the entire universe, he suggested that space and time form a closed surface without edges or endpoints. Think of the surface of the Earth. You can walk in any direction and never reach a boundary or a final destination. In the quantum state of the early universe, time effectively loses its linear character and behaves as an additional spatial dimension. In this regime, the distinction between the beginning and the middle vanishes. The universe does not have a singular point of creation, it simply is. It exists as a self-contained entity that requires no external conditions to initiate its development. This framework eliminates the need for an antecedent time because the geometry of the universe is finite yet unbounded. We are left with a cosmos that is entirely self-sufficient, requiring no prior state to explain its existence, effectively silencing the question of what came before by demonstrating that the concept of a beginning is merely a projection of our limited perception. We have explored the notion of a universe that stands as its own cause, defying our intuition about beginnings and endings. Whether we view the Big Bang as a hard limit on causality or as a gateway within an infinite cycle, we are forced to confront the limits of human cognition. The no-boundary proposal invites us to perceive reality as a closed, consistent structure where the past is not a line leading to a start, but a feature of the cosmic geometry itself. As we push the boundaries of what the James Webb Telescope and gravitational wave detectors can reveal, we are constantly reminded that our bubble of observation is growing, yet the ultimate mystery remains beyond our reach. The history of the universe is a library vast beyond our comprehension, and we are still reading the first few pages. Perhaps the most profound truth is not that we have the answers, but that we have reached the point where the questions themselves have forced us to redefine the very nature of existence and time. The next time you gaze at the night sky, remember that you are looking at a story that has no beginning, only an endless unfolding of possibilities that exist regardless of our capacity to witness them. We are part of this infinite, self-contained architecture, and our curiosity is the universe finally understanding its own history. Imagine standing on a silent beach where the tide does not just pull back but vanishes, carrying away the very ground beneath your feet. You are inside a bubble of light, a sphere spanning 46 billion light-years defined by the age of the universe. This bubble is the observable universe, a vast collection of 2 trillion galaxies containing countless stars and mysteries. Yet, this view is a grand deception. What you see in the night sky is not a live feed of the present. It is a photographic archive, a collection of layered times where light from distant eras arrives simultaneously. The speed of light acts as a limit, a fundamental constraint that defines the causal horizon of our existence. You are currently looking at ghosts, remnants of celestial objects as they were billions of years ago. The universe appears static and permanent to our senses, but this is a structural impossibility. At this very instant, the cosmos is active, evolving in ways that remain forever beyond our reach. We live in a narrow window of cosmic time where the evidence of our origins is still accessible. Beyond this invisible sphere lies a reality that exists right now, but remains permanently unobservable. We are situated observers trapped inside a bubble of information, limited not by the quality of our telescopes, but by the geometry of time and space. The reality we access is merely a delayed version of a history that has already unfolded. For decades, cosmologists viewed the cosmos as a dance governed by gravity. If you throw a stone into the air, it slows down until it falls back. Astronomers once applied this intuition to the entire universe. Since the Big Bang, all matter has been rushing outward. Logic dictated that gravity, the attractive force of all stars and galaxies, would eventually reign in this expansion. The expectation was clear: the rate of expansion must be decelerating. Calculations suggested that the universe might eventually stop growing and perhaps collapse in a final event known as the Big Crunch. This vision provided a comforting sense of order and eventual resolution. Gravity was supposed to be the architect of the cosmos, the force that keeps the cosmic dance from becoming too wild. Every galaxy felt the pull of its neighbors, a constant drag on the initial impulse of the Big Bang. This was the foundation of our understanding, a universe with a measurable history and a predictable fate, where expansion was a runaway process being steadily tamed by the heavy hand of gravitational mass. We believed the expansion would continue indefinitely but at a perpetually decreasing rate, as if the universe were a traveler running out of breath, inevitably settling into a state of graceful, slowing rest, forever bound by the inherent pull of its own structure and contents. Physics, however, keeps secrets that defy our intuition. In the late 90s, observations of distant supernovae shattered the expectation of a slowing universe. The results were not just different, they were the polar opposite of what the math suggested. The universe is not being held back, it is being pushed. We have entered the era of dark energy, a mysterious, repulsive force that dominates 68% of the cosmos. This dark energy does not attract, it repels space itself. It acts like an invisible engine, forcing the fabric of spacetime to grow ever faster. Galaxies are not merely moving through space, the space between them is stretching at an accelerating rate. For galaxies beyond a certain threshold, this expansion ensures that their light emitted today will never reach us. The bridge between us and them is growing faster than any signal can walk. This threshold, the cosmological event horizon, is a frontier that moves away as we approach it. We are not seeing a static landscape, but a receding one. The galaxies we catalogue are not just distant, they are fleeing. The acceleration of this expansion means that the lake of the observable universe is slowly evaporating. Light that left those galaxies when the universe was younger and less stretched managed to reach us, but their present state is already locked in a territory that is permanently silent to us. The light emitted right now will travel forever towards us and never arrive, lost in the stretching vacuum of an accelerating cosmos. The synthesis of these forces creates a chilling prospect for the long-term history of our existence. The observable universe is a window, not a room, and that window has edges determined by physics. Accelerated expansion creates a cosmological event horizon that traps us within a bubble of solitude. As dark energy continues to dominate, our causal connection to the rest of the universe gradually severs. Galaxies are not vanishing, they are crossing into an inaccessible layer of reality. Observers in the distant future will see a radically impoverished sky compared to the richness we witness today. The filaments, the superclusters, and the billions of galaxies will gradually cross the horizon, disappearing one by one into the silence. We are currently living in a unique window of time, a period when the evidence of the Big Bang and the vastness of the cosmos remain visible. In the future, this evidence will be erased. The universe is silently storing its contents in rooms that no longer have entrances. This creates a state of structural solitude where each region of the cosmos converges towards isolation. Our observable universe is a bubble that is drifting toward an ultimate state of cosmic loneliness. We are the witnesses of a brief, brilliant epoch where the history of everything is still within reach, before the accelerating expansion transforms our vast cosmic neighborhood into an isolated, lonely island in an empty sea. We find ourselves as the only known form of organized matter capable of detecting and describing this horizon. We are not the center of the universe, but we are the universe folded back on itself, producing the capacity to wonder what it is. The fact that the universe is larger than any possible confirmation does not invalidate our observations. It reinforces the precision of our methods. We live in a privileged moment where the history of the cosmos is still readable. The horizon is not a prison, it is a framework that forces us to focus on the mysteries we can still hold. Within our bubble of 46 billion light-years, there remains more complexity than any civilization could explore in multiple lifetimes. The uncertainty regarding what lies beyond is not a flaw in our science, it is a fundamental property of the cosmos. Reality does not require a witness to be real. It does not wait for us to understand it before it unfolds. The absence of information from beyond the horizon is not a lack of existence, it is an absence of connection. We are the instrument through which the cosmos becomes aware of its own limits, recognizing that the window of opportunity is narrow. The night is quiet and the horizon is immense. We stand at the edge of what can be known, looking into a silence that has existed since the beginning of time. This is not the end of our journey, but the point where we learn to appreciate the light that still reaches us. When you look up at the night sky from a place with little light, you see a pale, whitish band of stars stretching across the dark. This is the Milky Way, a spiral galaxy containing approximately 400 billion stars. For centuries, humanity saw this band of light as a static and unchanging decoration of the cosmos. Yet, our current understanding is shifting. We are no longer mere observers trapped within one of its spiral arms, we are data collectors deciphering a map of our cosmic home. The Gaia mission has changed everything, providing an unprecedented view of our galaxy. By cataloging nearly 2 billion celestial objects and performing 3 trillion observations, Gaia transformed static images into a vibrant 3D portrait of our galaxy. We are about to uncover how this massive collection of stars, gas, and dust behaves, moving beyond the simple intuition of a quiet road in the sky to reveal the violent and beautiful history etched into our galactic neighborhood. Prepare to see the Milky Way as it truly exists, a colossal, living, and breathing system of light and motion. The common perception of the Milky Way is that of a tidy, symmetrical spiral galaxy. This view describes a core bulge filled with old, reddish stars, surrounded by a flattened disk organized into distinct, predictable spiral arms. In this model, our galaxy functions like a massive cosmic clock, with stars following smooth, circular orbits around a central gravitational anchor. The disk appears thin, flat, and stable, serving as a permanent home for the Sun and billions of other stars. This architectural vision portrays a static elegance, where the arms are fixed structures carved out by consistent rotation over billions of years. Astronomers once believed there were only 2 major spiral arms, with the rest of the galaxy acting as a simple, harmonious backdrop for the solar system. This tidy arrangement provides a comforting, orderly image of our galaxy. We feel secure knowing our place within this well-defined structure, imagining that the Milky Way has existed in this exact configuration for nearly the entire history of the universe. It is a portrait of stability, order, and persistent, quiet evolution that keeps the galaxy together as a coherent, unchanging unit. However, the data provided by the Gaia mission reveals a reality that defies this static stability. Our galaxy is not a well-behaved clockwork system, but a deformed and oscillating structure. The galactic disk is not perfectly flat, it is warped and twisted, moving like a spinning top that wobbles with immense energy. Hidden forces are continuously pulling and tugging at our galaxy, forcing it into complex shapes we once considered impossible. Furthermore, Gaia has identified the Radcliffe Wave, a gigantic undulating structure of gas stretching 9,000 light-years across our neighborhood. We are literally surfing on this massive ripple, which contains millions of times the mass of the Sun. This implies that the Milky Way is an arena of constant change, shaped by historical and ongoing collisions with smaller systems like the Sagittarius dwarf galaxy. These encounters have ripped stars away, compressed gas clouds, and triggered sudden, massive bursts of star formation that accelerated our galactic evolution. The spiral arms are not permanent, fixed highways, they are fleeting patterns that migrate and evolve as gravity disrupts the balance. Our galaxy is a landscape of chaos, where every collision rewrites the structural rules of our home. The truth of our cosmic neighborhood lies in this friction between the perceived order and the experienced chaos. We must accept that the Milky Way is a fluid system, a dynamic ecosystem where the grand spiral shape is a momentary outcome of long-term gravitational negotiations. The spiral arms are not static paths, but manifestations of gas and dust being compressed by the interplay of rotation and galactic encounters. We are residents of a galaxy that acts as a vast gravitational engine, where collisions with dwarf galaxies do not just cause destruction, but actively drive the birth of new stellar generations. The Sun itself was born during one of these accelerated phases of star formation triggered by a galactic interaction. By analyzing the proper motion of stars, we see a galaxy that is breathing, with parts of it flowing inward toward the core while other regions are being flung toward the edges. This synthesis reveals a galaxy that is never quite finished, its current structure is merely a chapter in a much longer narrative of assimilation and growth. The galaxy is a colossal, fluid machine that constantly recycles its matter to maintain its existence, proving that complexity is the hallmark of our galactic evolution. Understanding the Milky Way requires us to move past the desire for simple, static labels. We live within a system where the disk wobbles, the gas ripples, and the stars move in intricate dances determined by gravity's long reach. The Gaia mission has been our greatest instrument for this enlightenment, proving that even a massive galaxy is sensitive to the smallest tugs from passing neighbors. As we look at the maps generated by our recent technological efforts, we see the fingerprints of every interaction that occurred over the last billions of years. The Milky Way is our home, yet it is a home that is constantly under construction, reshaped by forces that span thousands of light years. We have traveled from a naive understanding of a simple spiral to the recognition of a complex, interacting giant. This knowledge does not diminish the beauty of our galaxy, it enhances it, showing us that we belong to a dynamic process that has been ongoing since the dawn of time. We are witnesses to a cosmic masterpiece that is still being painted, constantly evolving, and forever surprising those of us who take the time to map its motion. The mystery remains open, and each new update from our deep space probes will only prove how deep our connection to this shifting, beautiful structure really goes. Picture a world drifting silently through the deep lanes of the Milky Way, millions of light-years from the warmth of any parent star. No sunrise ever breaks the horizon, no seasonal rhythm marks the passage of a year, and the sky is a permanent expanse of obsidian black, studded with distant, uncaring stars. These rogue planets, or free-floating planetary mass objects, are the loneliest wanderers in the galaxy, tossed out by the chaotic gravity of their birth systems or born from clouds too small to ignite. How can a world without a central sun possess the conditions for habitability? We often look at the universe through a lens of solar reliance, believing light is the only engine of survival. But the cosmos holds vast, hidden regions where the rules change entirely. Tonight, we peel back the layers of cold ice to uncover whether life requires a star to exist or if the universe hides a warmer, secret reality beneath the surface of the dark. The conventional view of habitability is anchored to the habitable zone of a star, the specific distance where surface liquid water exists through solar radiation. Life as we know it, specifically photosynthesis-driven ecosystems, depends on the influx of stellar photons. On Earth, the sun is the architect of our climate, fueling photosynthesis, driving weather cycles, and dictating the rhythm of biology. Without the steady spotlight of a sun, the surface of a rogue planet loses all energy to the void. Heat radiates into the vacuum, oceans freeze from the top down, and the atmosphere collapses into snow and frost. A planet without a host star is a graveyard for surface life, as the temperature plummets to absolute zero and any potential biosphere loses its primary source of energy. If the star is the heart of a planetary system, its absence implies a frozen, stagnant death where evolution is impossible because the fundamental thermodynamic inputs are denied to the surface environment. However, physics offers a different perspective when we look beneath the surface. Planets are not merely shells waiting for solar warmth, they are dynamic machines of internal energy. A rogue planet retains the heat of its own formation, a residual glow from the violent collapse of gas and dust. Deep within the rocky mantle, the decay of radioactive elements generates a steady, long-term supply of geothermal energy. If a planet is large enough, or if it carries moons that flex under tidal gravity, this heat can migrate upward. An ocean trapped under a thick crust of ice is not necessarily a frozen block. Instead, the ice serves as an extraordinary insulating blanket, trapping internal warmth and maintaining a liquid layer in the dark depths. Hydrothermal vents, fueled by the planet's internal pressure, create chemical gradients where life could thrive on mineral-rich fluids. In this model, the surface is hostile, but the subterranean ocean becomes a protected cradle, immune to the absence of starlight. The gap between these perspectives narrows when we redefine the source of life-sustaining energy. The dependency on photosynthesis is a specific strategy of terrestrial surface life, but it is not the only pathway for biology. In the dark, starless reaches of space, chemistry and internal heat replace the sun as the drivers of metabolism. Habitability becomes a function of insulation and chemical disequilibrium rather than orbital distance. Rogue planets serve as independent energy systems where the internal heat leaking from the core mimics the stability of a habitable zone. A hidden ocean, enriched by hydrothermal interactions at the seafloor, acts as a closed-loop biosphere. The absence of solar input is not a total failure of energy, it is a redirection of energy flow from external radiation to internal chemical transformation. Life in these niches would be slow and microbial, yet it demonstrates that biological potential persists far beyond the reach of any stellar lighthouse. The existence of these wandering worlds challenges us to expand our definition of home in the cosmos. Rogue planets prove that even when a world is stripped of its sun and exiled into the silent dark, it remains a product of the same physical laws that govern our own solar system. Gravity, thermodynamics, and geology do not switch off when a planet departs its star. By peering into these cold, dark shells, we find that the galaxy is likely teeming with subsurface oceans, each a potential laboratory for life that has never known a sunrise. We are learning that the universe is far more inventive than our simple model suggested. Whether life exists in those hidden seas remains one of the most profound unanswered questions, but the fact that the conditions for complexity persist in the dark is a realization that changes everything. We are not just looking at a graveyard of planets, we are looking at a vast, unexplored frontier of potential life that survives in the patience of the interstellar void. The night sky is not a static portrait of the cosmos but a complex photographic archive of eras long past. When you gaze at the stars, you are not witnessing the present reality of distant objects, but rather a delayed message delivered with the punctuality of light. This fundamental limit, defined by a speed of 300,000 kilometers per second in a vacuum, transforms every observation into an act of temporal archaeology. Because the universe is 13.8 billion years old, there exists a horizon beyond which no information could have reached us since the Big Bang. This observable universe, a bubble 93 billion light-years in diameter, acts as a window to the past. However, we must consider if this window represents the entirety of what exists or if we are merely trapped within a local region of space-time. Does the speed of light define the ultimate boundary of existence, or does the universe contain realities that are permanently shielded from our sight, existing in a present we will never share? Traditional cosmology relies on the assumption that time serves as an absolute, uniform scaffolding, holding the cosmos together in a coherent, chronological sequence. If we were to rewind the film of the universe, like an old tape, we would theoretically trace every event back to a single point of origin 13.8 billion years ago. This perspective suggests that space and time are the reliable stages upon which the drama of matter and energy unfolds. By assuming a universal clock, we calculate the age of the cosmos and the distance to the furthest galaxies with mathematical precision. This linear view provides the comfort of a structured reality, where events follow a predictable cause and effect chain. If time acts as a constant, then our current observations, despite the light travel lag, allow us to reconstruct a singular, definitive history of everything that has ever transpired, from the first spark of creation to the complexity of the star systems we observe in our local neighborhood today. Physics tells a different story once we peer into the heart of extreme environments, where gravity distorts the very fabric of existence. Within the intense gravity of a black hole or the extreme density of the early universe, time ceases to act as a reliable anchor. Space and time form a continuum, a fabric that bends, stretches, and warps, rendering the concept of a universal now entirely obsolete. If you compress all matter into a singularity, time itself becomes so distorted that the notion of a beginning loses all coherence. General relativity dictates that time is not independent, and without a clock that ticks at a constant rate for every observer, the idea of a shared history across the cosmos begins to fracture. The expansion of space adds another layer of complexity, as galaxies recede from one another faster than light, permanently severing connections between different regions. Here, the universe reveals its true face, a collection of isolated stories unfolding in different temporalities, forever untethered from one another. The resolution to this paradox lies in understanding that time functions as a selective filter rather than a universal container. The observable universe is not a wall of darkness, but a horizon of causality delimited by the geometry of accelerated spacetime. Dark energy forces the universe to expand at an increasing rate, creating a cosmological event horizon that pushes galaxies beyond our reach forever. This means the present of the universe is permanently fragmented. What happens in a galaxy currently emitting its last visible light is an event we will never truly experience. The observable window, defined by the particle horizon, provides only the information that had enough time to reach us since the beginning. Consequently, we exist within a bubble of accessible reality while being surrounded by an immense, unknowable expanse. Time acts as the gatekeeper of our knowledge, deciding what enters our field of vision and what is locked away in rooms where no signal can ever cross. We find ourselves in a privileged moment of cosmic history, where the light of distant galaxies still manages to penetrate the darkening reaches of our bubble. This window of opportunity allows us to map the history of 2 trillion galaxies, though we are aware that this count is but a fraction of a much larger, unreachable reality. As dark energy continues to dominate, the universe slowly closes in on itself, pushing more distant regions beyond the threshold of observation. The realization that our knowledge is limited by the structural properties of space and time is not a defeat of the scientific method, but the ultimate expression of its maturity. We have identified the edges of our window and understand why they are impenetrable. The cosmos does not require a witness to be real, nor does it need to be fully visible to exist in all its majesty. We are the way the universe observes its own constraints, standing at the center of a horizon that moves with us, forever watching a past that can never be reconciled with the present. The night sky holds a secret that only the most precise instruments can whisper. We perceive stars as eternal beacons, yet many are ticking clocks counting down to a violent end. Deep in our galaxy, objects exist in a state of suspended agony, poised on the knife edge between stable existence and an irreversible plunge into the abyss. This is the story of J0952, a pulsar rotating at staggering speeds, and the silent pressure building within its core. What happens when the fundamental laws of quantum mechanics fail to hold back the relentless pull of gravity? We are witnessing the cosmic equivalent of a time bomb, a stellar relic that refuses to remain static. The balance is not merely fragile, it is nearing its absolute conclusion. As this mass grows, it approaches a threshold that science calls the Tolman-Oppenheimer-Volkoff limit. Will the structural integrity of the neutron star endure, or are we on the verge of seeing a new black hole being born in real time? The answer lies in the intense gravitational dance of a black widow system. Consider the scale of this impending event. We are not watching a distant, slow-moving nebula, but a rapid, localized explosion of physics occurring just 2,000 light-years away. Every millisecond, the pulsar steals matter from its companion, pushing itself closer to a final, catastrophic transformation. The vacuum between stars is suddenly not just an empty void, but a theater of extreme gravity. Prepare to explore the physics of the ultimate collapse. For decades, our understanding of the cosmos suggested that neutron stars represented the final, stable stage for massive stellar remnants. Once a core collapses and the protons and electrons merge into a sea of neutrons, the resulting pressure of degeneracy should be enough to stop the contraction. This quantum force acts as a rigid, impenetrable floor, preventing further reduction in size. In this view, a pulsar like J0952 would simply continue its existence, spinning and emitting radiation for billions of years without significant change. It is a comforting model of permanence in a chaotic universe, suggesting that even the most massive stars leave behind a predictable, unchanging corpse. We observe these objects as incredibly dense spheres, maintaining their identity even when they are cannibalizing their companions. The mass they accumulate was thought to be inconsequential, mere surface noise compared to the massive stability provided by the neutron lattice. If this model were absolute, the universe would be filled with these ultra-dense structures, all comfortably resting at their fixed radii. This paradigm assumes that gravity has reached a state of checkmate. The laws of nature, in this perspective, have created a finality, a point where matter simply refuses to be crushed further. The pulsar represents the ultimate victory of quantum resilience over the infinite appetite of massive bodies. We rely on this stability to categorize the stars, assuming that once the journey to neutron status is complete, the destination is fixed for eternity. Nature, however, does not always adhere to our desire for stability. The existence of J0952 shatters this perception of static permanence. This pulsar is rapidly exceeding the mass thresholds that our previous models deemed safe. Gravity, in its relentless pursuit of density, does not settle for a quantum floor if the pressure becomes great enough. The Tolman-Oppenheimer-Volkoff limit serves as the ultimate barrier. Once surpassed, the neutron degeneracy pressure is fundamentally insufficient to withstand the sheer curvature of spacetime. In this extreme environment, the very particles that constitute the star are forced into a state of structural defeat. J0952 is currently gaining mass from its companion at an alarming rate, and recent observations show that the pulsar is already within a tenth of a solar mass of the critical breaking point. We are not looking at a stable object, but at a transition state that defies the old narrative of stellar finality. The pulsar is currently spinning at 700 rotations per second, creating a centrifugal buffer that barely keeps the structure intact. Yet, this rotation is a fleeting defense against a doom that has been mathematically codified. When gravity finally succeeds in forcing the material beyond the limit, the collapse will occur in less than 1 millisecond, a blink of an eye in cosmic time. The quantum barriers, once considered absolute, are merely temporary obstacles in the path of a collapsing singularity. This is the reality of extreme evolution. There are no permanent endpoints, only stages of increasing density. The transition from a pulsar to a black hole is a process of extreme physical metamorphosis. It is not an end, but a radical transformation of matter and space. When the pressure of degeneracy fails, the star ceases to be a material object in the conventional sense and enters a domain governed by pure curvature. The sudden collapse creates a singularity, a point where the equations of general relativity reach infinity, effectively stripping the matter of its identity as a physical star. We see this through the emission of gravitational waves, which are ripples in the fabric of the universe itself. These waves carry the signal of the collapse, signaling to the cosmos that a new black hole has emerged. This event acts as a natural laboratory, allowing us to test the equation of state for ultra-dense matter. Does the matter inside pass through a phase of quark-gluon plasma before collapsing completely? Does it become strange matter, supporting the structure slightly longer than expected? By studying J0952, we are probing the boundaries of nuclear physics. The collapse is the ultimate manifestation of the conflict between quantum mechanics and gravity, a conflict where gravity is the inevitable victor. We are transitioning from a universe that contains matter-based remnants to one that contains pure gravitational anomalies. This process provides the evidence necessary to finalize our models of stellar evolution, confirming that the path from massive star to black hole is a continuum of ever-increasing density. We are standing on the threshold of witnessing an event that has never been directly observed by humanity. The birth of a black hole from a known stellar progenitor is the holy grail of modern astrophysics. If J0952 collapses within the next few centuries, our gravitational wave detectors will capture the signal of a star transforming into a singularity. This discovery will finalize the debate regarding the stability of neutron stars and the nature of extreme density. We learn that the universe is not made of fixed objects, but of evolving systems that respond to the basic forces of nature. The story of J0952 is a reminder that even the most massive, resilient objects are subjected to the fundamental laws of gravitation. As we look at the Milky Way, we see a theater of transition where stars are born, die, and sometimes vanish into the dark. Humanity is the witness to this grand evolution, using the light and waves captured by our machines to map the limits of existence. Whether these pulsars survive or collapse, they serve as the markers of a cosmos that is in constant, dynamic flux. The dark is not empty, it is populated by the remnants of stellar stories that continue to unfold far beyond our immediate reach. The collapse of a neutron star is not just the loss of a star, but the formation of a gateway into the most mysterious regions of spacetime. We wait, we watch, and we observe, knowing that one day, the Black Widow will finish its meal and the light will flicker out forever. The universe tells a story of expansion that traces back to a moment of breathtaking intensity. Imagine rewinding the cosmic film, compressing galaxies, stars, and atoms into an infinitely small point, a singularity where the laws of nature as we comprehend them seem to buckle under their own weight. This is the starting line of our observable universe, a concept that challenges the very architecture of time and space. When we gaze into the night sky, we are not seeing the present, but the echoes of a distant, cooling past. The Big Bang is not just a theory, it is the mathematical inevitability that arises when we reverse the motion of the cosmic expansion. Yet, this beginning remains shrouded in mystery, sitting at the intersection of what we can prove and what we can only speculate. If we strip away the layers of cosmic evolution, what remains at the core of this primordial void? Are we looking at a wall that cannot be breached, or merely the threshold of a new scientific paradigm? The answer depends on how we define the limits of reality itself. Consider the perspective that the Big Bang emerged from a physical singularity, a point where the entire mass and energy of the cosmos were unified. In this framework, the equations of general relativity are not just suggestions, they are the governing principles that held sway even at the dawn of time. If we accept this premise, the singularity is not an error in our calculations but a literal point of origin where the fabric of spacetime was compressed into a state of infinite density. Albert Einstein, Edwin Hubble, and Stephen Hawking provided the foundation for a universe that began from this singular, dense state. By rewinding the expansion, we arrive at a moment where time and space were inseparable, forming a continuum that dictates the evolution of every star and galaxy we see today. Within this dense cradle, all the physical constants that rule our existence were set into motion, acting as the boundary conditions for a universe that would eventually bloom into the vast, complex structure we inhabit. It is a bold, unified vision of a reality that has a clear, defined starting point in our history. However, the singularity might be less of a physical destination and more of a warning sign that our current theories are incomplete. The mathematical appearance of infinity at the beginning of the universe often suggests that the laws of physics are breaking down rather than functioning at their peak. Many physicists argue that describing the birth of the universe with traditional general relativity is like trying to map the ocean floor with a ruler. It works for a while, but eventually, it misses the true structure of the deep. If we invoke quantum mechanics to describe that same primordial era, the singularity vanishes, replaced by a quantum foam or a state where time itself loses its meaning. In this view, our current understanding of spacetime is a limited approximation, a local rulebook that fails to account for the extreme energy densities of the absolute beginning. Suggesting that the singularity is a physical reality ignores the potential for new physics, such as string theory or loop quantum gravity, which may redefine the transition from nothingness to somethingness. We are likely staring at the limitations of our own intellectual reach. Perhaps the singularity is neither a simple physical point nor a total failure of theory, but rather the bridge between what we understand and what remains hidden. It serves as the transition point where the observable cosmos shifts from a state of total unification to the structured expansion we observe. By framing the singularity as a boundary condition, a state without an initial start in the traditional sense, we can reconcile the fluidity of time with the necessity of an origin. Imagine space existing without time, a state where causality is not yet defined, effectively removing the paradox of what came before. This transition allows for the universe to emerge from a state of infinitesimal density without requiring a tick-tock clock to mark the start of its journey. We are looking at a process of cosmic unfolding where the rules of the game are written as they are played. This perspective invites us to view the beginning not as a moment of creation in a vacuum, but as a phased transition of reality itself, shifting from pure, compressed potentiality into the unfolding history of stars, galaxies, and observers. The mystery of the primordial moment is the most profound challenge left for human inquiry. Whether the beginning was a singular point or a complex quantum event, it remains the anchor of our existence. We are the witnesses of a process that started 13.8 billion years ago, a history etched in the cosmic microwave background and in the light of distant galaxies. While we may never physically travel back to that era, our ability to formulate the question proves that we are intimately connected to that moment. The quest to understand the origin of the universe is, in essence, the quest to understand our own place within it. As we push the boundaries of what is observable, using tools like the James Webb Space Telescope and gravitational wave detectors, we move closer to the veil of the unknown. We exist in a unique window of cosmic time where the evidence of our origin is still reachable. Even if the singularity remains forever just beyond our grasp, the pursuit itself is what defines our civilization. We are the universe peering back at its own beginning, forever searching for the truth that lies just beyond the reach of the observable horizon. The Milky Way looks like a static beacon of stability in the dark expanse of the night. From our perspective on a quiet spiral arm, the galaxy seems to be a settled arrangement of stars, gas, and dust governed by its own internal rhythm. We perceive the swirling structure and the brilliant core, assuming that this architecture is the result of a long, lonely, and peaceful evolution. The galaxy behaves like a clockwork mechanism, where gravity orchestrates the dance of stars in perfect isolation. This image of serene independence is comforting because it suggests a predictable history for our solar system. However, the true nature of our galactic home is far more violent and interconnected than the visible disk suggests. Deep beneath the surface of this apparent tranquility lies a secret history of chaos, disruption, and rebirth that our ancestors could never have suspected. The galaxy is not a finished masterpiece, but a canvas that is constantly being repainted by unseen cosmic forces from the darkness beyond our immediate reach. Traditional models of galaxy formation often emphasize internal stability as the primary driver of structure. In this view, a galaxy emerges from the gravitational collapse of primordial gas, following a deterministic path dictated by its initial mass and angular momentum. Stars form when giant molecular clouds reach a critical density and ignite, and this process unfolds in a predictable, isolated environment. The galaxy manages its own destiny, with feedback mechanisms regulating the pace of star birth and the distribution of stellar populations. Proponents of this static evolution argue that the spiral arms and the central bulge are primarily products of internal disk dynamics and standard thermodynamic cooling. If a galaxy remains undisturbed, it should settle into a permanent, balanced state where star formation gradually slows as the supply of cold gas is exhausted. This perspective portrays galaxies as solitary giants that grow old and fade, governed entirely by their own internal properties and the steady pull of their own gravity, free from external interference. Interactions between galaxies are not mere accidents, they are powerful engines that reconfigure the entire galactic landscape. When a dwarf galaxy approaches, its gravitational influence ripples through the Milky Way like a stone cast into a still pool. The Sagittarius dwarf galaxy has engaged in repeated collisions with our home, piercing the thin disk and stirring up the gas within. These encounters compress vast reservoirs of interstellar medium, triggering waves of star formation that would otherwise never happen. This process is a fundamental necessity for maintaining the galaxy's vitality, ensuring that gas is not just static, but dynamic and productive. The compression of gas serves as a trigger that accelerates star birth by factors that the internal model fails to account for. Without these dramatic encounters, the Milky Way would be a much older, fainter, and more sluggish place. Collisions are not just destructive events, but necessary catalysts that maintain the galaxy's cycle of renewal and prevent it from prematurely entering a state of dormant senescence. The evolution of the Milky Way is a complex, collaborative phenomenon where internal processes and external forces interact in a delicate feedback loop. Gravity does not distinguish between a galaxy's own material and the gas brought in by an intruder, it treats all density increases as opportunities for star creation. A galaxy is a living ecosystem that requires the influx of new dynamics to sustain its spiral structure and its rate of star formation. The spiral arms themselves are maintained by a combination of internal rotation and the gravitational perturbations induced by passing companions. Therefore, we should view the galaxy as a dynamic entity that exists in a constant state of exchange with its environment, where the boundaries between one system and another are perpetually blurred by gravitational tidal forces. This synthesis reveals that galactic life is essentially defined by a history of encounters, where the density of stars and the life cycle of gas are fundamentally written by the history of every collision that the galaxy has ever endured. Understanding our home requires us to accept a reality that is far more active than the view from our own telescope might suggest. We are not lonely voyagers in a dead sea, but active participants in an ongoing narrative of collision and convergence. The Milky Way owes its current brightness and structure to the intruders it has met and consumed over the last 5 billion years. Each encounter has left its mark, fueling the birth of stars and maintaining the spiral integrity of the disk. This perspective invites us to look at the night sky not as a static painting, but as an active construction site where every ripple of gas and every wandering cluster tells a story of survival. We have discovered that the cosmos is a web of interaction, where the fate of one system is inextricably linked to the movement of others. The history of the Milky Way is the history of its meetings, and our future will inevitably be shaped by the encounters yet to come in the vast and silent dark. The night sky is a grand theater where light plays the leading role, yet we are witnessing only a tiny fraction of the show. We gaze at stars, nebulae, and glowing galaxies, convinced that what we observe constitutes the sum of existence. We measure the universe by what can be captured by our lenses and mirrors, assuming that matter must reveal itself through brilliance. But this perspective is a profound deception born of our biological constraints. We are trapped in a narrow band of the electromagnetic spectrum, perceiving only the energy that burns bright enough to pierce the void. Beyond this thin veil lies an immense, silent architecture of the cosmos that remains permanently hidden from traditional telescopes. What if the true substance of the Milky Way is not the light we celebrate, but the darkness we ignore? We are about to explore a reality that defies our most basic assumptions about scale and presence, where the most massive structures are defined by what they emit rather than what they radiate. The common perception is that the observable universe is a perfect map of all that exists, because matter, in its most fundamental state, must eventually interact with light. We believe that if an object exists, it should possess a signature, a glow, or at least a reflection of a distant sun. From the smallest asteroids to the most massive galaxy clusters, we expect everything to be illuminated. We rely on the speed of light as our messenger, confident that it will eventually carry information from the farthest reaches of space to our sensors. We assume that the darkness of the void is merely a canvas for the stars, a neutral background waiting to be filled by stellar radiance. This belief creates a sense of comfort. It tells us that our instruments are enough, that with enough patience and technology, we can catalogue every grain of dust in the galaxy. We define reality by visibility, trusting that nature has no secrets that cannot be coaxed into the light. This reliance on visible light is a massive miscalculation that misses the majority of the cosmic puzzle. The reality of the universe is dominated by phenomena that explicitly avoid the light, rendering our traditional telescopes blind to their true extent. Consider the rogue planets, those wandering worlds that drift through the dark lanes of the Milky Way without a parent star to reveal their shape or warm their horizons. They do not shine, nor do they reflect sunlight. They are nearly invisible pebbles in a dark ocean. Consider the dormant black holes, gravitational monsters like Gaia BH3, which consume nothing and emit no radiation, hiding in the void like silent predators. These are not rare aberrations, they are systemic components of the galaxy. Dark energy drives the acceleration of cosmic expansion, pushing structures beyond our event horizon, while vast waves of gas remain largely unseen until mapped by the statistical precision of missions like Gaia. The universe is not a catalogue of lights, it is an ocean of shadow where light is the exception. We find ourselves living in a reality defined by a profound asymmetry. Our human experience, and consequently our entire scientific history, is tethered to the photons that reach our eyes, yet these photons are merely the messengers of the most energetic and volatile processes, not the most abundant. The synthesis of this reality is that the cosmos is a hybrid of the visible and the invisible, where the most massive architectures, the dark matter halos and the silent drifting populations of rogue planets, act as the invisible scaffolding for the stars. We are beginning to realize that the light we measure is the surface, while the darkness is the depth. To understand the universe, we must stop asking what we can see and start asking what we can detect through gravity, motion, and the subtle warping of spacetime. The reality of the cosmos is not limited to our field of vision, it extends into a vast, cold expanse where structures exist without radiation, evolving through eons in a state of eternal, silent isolation. The realization that our universe is fundamentally opaque humbles our place in the cosmic order. We are not total observers, but rather situated witnesses within a bubble of time, seeing only what the speed of light permits. Every star, every galaxy, and every distant nebula we catalogue is merely a temporary signal in a sea of encroaching darkness. We are learning that the universe is larger than our ability to confirm it, and that its most significant phenomena are often those that defy the light. As we refine our instruments, we are not just adding more stars to our maps, we are slowly uncovering the massive, silent structures that define the fabric of existence. The future of science lies in embracing this invisible heritage, understanding that the dark is not an absence of reality, but a manifestation of it. We remain wanderers in a galaxy that hides most of its inhabitants in shadow, and perhaps that is the greatest mystery of all, to exist in a universe that remains, by design, largely beyond our capacity to fully perceive. Look up at the night sky. What you see is a flat, static painting, a collection of distant lights that seem fixed in the velvet of space. For millennia, humanity believed this was the whole reality, a dome of stars encircling our small corner of existence. We measured positions with naked eyes and later with modest glass lenses, constructing maps that were beautiful but fundamentally incomplete. We were like sailors lost in a vast ocean, trying to navigate by stars we thought were anchored to a wall, failing to realize the entire structure was in constant, silent motion. The truth is far more complex than our ancestors could have envisioned, and our initial maps were merely sketches on the surface of a depth that we were only beginning to measure. How can we truly understand the architecture of our home when we are trapped inside its spiral arms, unable to step back and look at the whole picture? The key to unlocking the Milky Way lies not in more glass, but in the precision of space-time measurements that define our current cosmic horizon. The history of astronomy is a story of patient, manual cataloging. For centuries, telescopes based on Earth, peering through the distortions of our atmosphere and the clutter of cosmic dust, provided us with a view that felt sufficient. By tracking the positions of celestial objects from a ground-based perspective, astronomers created the foundational catalogues that defined the modern cosmos. These maps, built upon parallax measurements and basic astrometry, allowed us to understand the general arrangement of the spiral arms and the position of our solar system within the galactic plane. It was a view that comforted us, giving the impression that we had conquered the space around us. We believed that with larger mirrors and longer exposure times, we could eventually piece together a complete 3D model of our galaxy. This methodology, relying on individual star observations, was the gold standard, providing the data that powered centuries of scientific progress and enabled us to construct the foundational laws of celestial mechanics that guide our understanding of the heavens to this very day. However, this terrestrial perspective is plagued by fundamental limitations. Our atmosphere acts as a veil, and our static ground-based position blinds us to the subtle, true movements of the stars. To map a galaxy of 400 billion stars, a mere frontal portrait is insufficient. We need precision that transcends human perception, a level of measurement that defines the difference between a static model and a dynamic reality. The Gaia mission represents a seismic shift, placing a telescope at the Lagrange point L2 to achieve astrometry with the accuracy of measuring a human hair from 1,000 kilometers away. By observing each star multiple times from different angles, we unveil a galaxy that is not flat, but deformed, oscillating like a spinning top, and rippling with gaseous structures like the Radcliffe wave. These movements, these complex orbital paths, and the hidden mass of dormant black holes are entirely invisible to traditional Earthbound observation. The true architecture of the Milky Way is a three-dimensional tapestry of energy and movement that can only be revealed through the cold, uncompromising precision of space-based astrometric measurements. When we combine this unprecedented accuracy with sophisticated computational models, we move from passive observation to active simulation. The Gaia mission has generated a treasure trove of data that functions as a living laboratory for galactic evolution. By processing trillions of observations, we track the proper motion of stars, allowing us to rewind time and witness the collision history of the Milky Way with the Sagittarius dwarf galaxy. This synthesis of precise data and 3D visualization reveals that our galaxy is not a static object, but a dynamic, evolving system, shaped by past encounters and hidden gravitational influences. We are now able to see that our solar system is effectively surfing on waves of stellar formation triggered by these ancient galactic interactions. The raw information from the mission is being transformed into a high-fidelity model that reconciles the positions, velocities, and chemical compositions of billions of stars, proving that the complexity of our home galaxy is far greater than any ground-based manual map could ever suggest or sustain. We have stepped out of the fog of our own localized perception and into the clarity of a new astronomical era. The Milky Way is no longer just a band of white light in the sky, but a vast, swirling whirlpool of history, motion, and hidden structure. Through the legacy of the Gaia mission, we have finally moved beyond the limitations of our internal position, capturing a map that reveals our galaxy as an intricate, evolving masterpiece. The challenge ahead lies in interpreting the future data releases that will continue to refine our understanding of this celestial mass we call home. We now know that our galaxy has been shaped by the interplay of hidden forces, gravitational tides, and the relentless dynamics of stars moving through the void. As we look at the stars tonight, the static painting has vanished. In its place, we perceive a complex, breathing machine of cosmic proportions, and we are finally beginning to understand the rhythmic pulse of the spiral arms that carry us through the dark. The horizon of our knowledge has expanded, and we are now better equipped to answer the fundamental questions about our origin, our trajectory, and our place within the vastness of the universe. The silence of the night sky hides a question that has haunted humanity for generations. We look at the stars and wonder if we are truly alone in this vast cosmic expansion. Recent advancements in astronomy, specifically through the James Webb Space Telescope, allow us to peer into the atmospheres of distant worlds, searching for the faint whispers of life known as biosignatures. This is not merely about finding a planet with the right temperature, it is about detecting the specific chemical fingerprints of existence itself. Are these molecules, such as methane or dimethyl sulfide, the smoking gun we have been seeking? We are now at a threshold where our technology finally touches the edges of what was once considered science fiction. By analyzing how light from a distant star interacts with a planetary atmosphere, we begin to decode the composition of worlds hundreds of light-years away. This journey into the unknown requires us to rethink our place in the galaxy, challenging our perception of life in the universe. The presence of specific chemical compounds in the atmosphere of an exoplanet constitutes definitive proof of biological activity. When we observe molecules like methane, water vapor, and especially dimethyl sulfide in the spectra of worlds like K2-18b, we are witnessing the metabolism of life on a planetary scale. On Earth, dimethyl sulfide is produced primarily by marine phytoplankton, acting as a biological marker that is difficult to replicate through non-living processes. If we detect such molecules in abundance, it implies that these compounds are being constantly replenished by living organisms. The complexity of these organic chains requires an engine, a biological furnace that maintains them against the entropy of space. To deny this evidence is to ignore the patterns of nature where chemical signatures consistently correlate with the presence of active, evolving biological systems. These signatures serve as the ultimate reliable beacon in our search for alien life. However, the universe is a master of mimicry, capable of creating complex chemical environments through purely abiotic means. Geology and photochemistry can simulate the signatures we associate with life, leading us toward potentially false conclusions. Methane, for instance, is produced in high quantities by volcanic activity and serpentinization, where water reacts with rock deep inside a planet. Furthermore, ultraviolet radiation from a host star can trigger atmospheric reactions that synthesize organic molecules out of simple precursors, creating a facade of biological richness where no life actually exists. If we rely solely on a single chemical indicator, we risk projecting our terrestrial biases onto environments that follow entirely different physical laws. The mere presence of a molecule is not a biological mandate, it is a chemical datum that could easily be the product of a planet's volcanic breathing or its interaction with stellar radiation, rather than the work of an organism. The path forward lies in integrating chemical data with the broader planetary context. A biosignature is not a verdict, it is a clue that demands corroboration. We must evaluate the planetary environment as a whole, considering its mass, its distance from the star, the composition of its surface, and the presence of liquid water. K2-18b, with its potential for an ocean covered by a thick atmosphere, demonstrates that we cannot interpret a single molecule in isolation. We need to measure the ratio of various gases to understand if the atmosphere is in chemical equilibrium. If we find methane, carbon dioxide, and dimethyl sulfide in a specific disequilibrium that geology cannot explain, the argument for life gains substance. Science does not seek the shortcut of a single molecule, but rather the convergence of multiple lines of evidence. This holistic approach ensures that we distinguish between the products of a dead, active planet and the artifacts of a living, breathing world. We are currently living in the most significant epoch of astronomical discovery in human history. The ability to detect biosignatures transforms the search for extraterrestrial life from a philosophical daydream into a rigorous, data-driven discipline. While the road is fraught with the danger of misinterpretation and the temptation of premature conclusions, the systematic study of exoplanetary atmospheres provides our best chance to answer the age-old question. Every new observation by the James Webb Space Telescope refines our understanding, pushing us closer to a definitive confirmation. Whether these chemical signals ultimately lead to the discovery of microbial ecosystems in deep, hidden oceans or reveal the complex, deceptive behaviors of young, active planets, the process itself brings us closer to the stars. The universe may remain silent, but through our instruments, we are learning to listen to the chemical language of existence. We are no longer just looking at the sky, we are beginning to read it, preparing for the day when the data finally confirms we are part of a living cosmos. Imagine standing at the center of an invisible bubble that grows more lonely with every passing second. You are surrounded by 2 trillion galaxies, each teeming with stars and silent stories, yet this entire observable sphere is merely a fragile slice of a much deeper reality. We are bounded not by walls, but by the relentless speed of light and the irreversible march of cosmic time. Every point of light you see at night is a messenger from a different era, a ghost of a star that might have already flickered out of existence. What happens if this bubble is not the whole story? What if the universe extends far beyond the reach of our longest-range telescopes, into a domain where the laws of physics might weave patterns we can never confirm? We are trapped in a light cone that only shows us a delayed version of a reality that has already evolved into something unrecognizable. The question is no longer just what we can see, but what kind of universe hides behind the veil of our own observational limitations. We are about to cross the threshold of our local cosmic bubble to investigate if we are living inside a finite, contained structure, or if we are merely small inhabitants of a vast, potentially infinite expanse where the improbable becomes inevitable. The most compelling physical evidence suggests that our universe is fundamentally finite, bound by its own energetic origin. If the cosmos were truly infinite, it would manifest paradoxes that contradict our local observations of a uniform, cooling expansion. A truly infinite universe would contain an infinite amount of matter and energy, which should exert an infinite gravitational influence on every point, creating a state of thermal equilibrium that would render the dark, starry skies we observe tonight physically impossible. Instead, we see a universe that started from a single point of infinite density, expanding outward for exactly 13.8 billion years. This age creates a hard, non-negotiable boundary, the particle horizon. We know this boundary is real because the cosmic microwave background radiation acts as a fog of last scattering, a wall beyond which light cannot travel to us because the universe was not yet transparent. If the universe were infinite, we would expect to see signs of this lack of a singular beginning, yet the precision of the Hubble constant and the structured nature of the light cones we measure point toward a finite, unfolding event. To assume an infinite universe is to ignore the structural impossibility of gravitational stability in a landscape of infinite mass, a contradiction that challenges the very foundations of the Big Bang model. However, the geometry of our cosmos tells a startlingly different story when we examine the curvature of space itself. Data from the Planck probe suggests that space is remarkably flat, with a margin of error so thin it forces us to reconsider the necessity of finitude. In a flat universe, there is no inherent geometric closure that forces the cosmos to curve back on itself, implying that space could continue indefinitely in all directions. If the universe is flat and truly extends without limit, the statistical implications are staggering. In an infinite expanse, the finite combination of particles must eventually exhaust all possible arrangements. This leads to the haunting possibility that patterns repeat themselves across the cosmic landscape. Somewhere, perhaps trillions of light-years beyond our observable horizon, an identical configuration of stars and planets might exist, hosting versions of events that we consider unique to our own bubble. The accelerated expansion driven by dark energy only deepens this mystery, pushing distant galaxies away from us faster than light can travel, isolating us into a local pocket. This acceleration does not imply the universe is ending, rather, it suggests that the total volume of the cosmos is so vast that our observable 93 billion light-year diameter is little more than a single, microscopic droplet in an infinite ocean of spacetime, where the repetition of matter is a mathematical necessity. The resolution to this conflict lies in recognizing that our inability to observe the whole does not define the limits of the whole. We are situated observers trapped inside an observable bubble of 46 billion light-years in radius, a window created by the age of the universe and the speed of light. This finitude is an observational constraint, not an ontological one. Whether the universe is finite or infinite remains a question that pure observation may never fully resolve, precisely because our horizon recedes as dark energy pushes the cosmos apart. The reality is that the universe may be a flat, infinite landscape where our bubble is merely one of countless regions undergoing similar processes of galaxy formation and stellar evolution. We inhabit a specific, local history governed by the same laws of physics that apply in the unobservable depths beyond our event horizon. The total universe is likely vastly larger than what our current instruments can probe, perhaps trillions of times larger or even truly infinite. By understanding that our bubble is a window and not a room, we reconcile the finite nature of our history with the potential infinite nature of space. The observable universe provides us with the raw material to understand the cosmic blueprint, while the unobservable expanse remains the silent theater where the same laws continue to play out on a scale that defies any human capacity to map. We find ourselves in a privileged moment of cosmic history, where the light from the early universe is still reachable and the signatures of the Big Bang are still imprinted on the sky. A trillion years from now, our distant descendants will see a vastly emptier sky as galaxies drift beyond the cosmological event horizon, permanently erased from their observational window. We possess a unique, narrow band of time to comprehend the scale of our existence. Whether the universe is a finite pocket of order or an infinite repetition of reality, its grandeur remains indifferent to our ability to witness it. We are the mechanism by which the cosmos has folded back upon itself to contemplate its own boundaries. The horizon is not a wall, but a testament to the depth of a reality that refuses to be fully captured by a single glance. As we continue to refine our maps and peer deeper into the infrared, we are not just measuring distances, we are learning the dimensions of our own cosmic solitude. The night sky is more than a map, it is an archive of past echoes, and the silent vastness beyond the horizon is the reminder that existence is always far larger than the information we are permitted to access. Look up tonight knowing that every point of light is a connection to a past that has already shaped you, while the dark spaces between them hold the potential of an infinite, unobservable expanse. What remains of a star when it vanishes into the absolute dark of a singularity? This is not merely a question of light, but of the very bedrock of physical reality. Deep in the heart of a collapsed stellar core, we face a cosmic erasure so profound that it threatens the foundation of our understanding. Imagine an object so dense that spacetime itself becomes a bottomless pit. When matter crosses the event horizon, we are told it enters a realm where gravity reigns supreme. Yet, there is a far deeper mystery hidden here, one that keeps physicists awake at night. If the universe operates on the preservation of information, what happens when a star falls into a black hole? Does the history of that star simply vanish, or is it merely locked away in a vault we cannot reach? This enigma challenges everything we perceive about cause and effect. It forces us to confront the silence left behind when the brightest light becomes the deepest void. We are standing on the precipice of a radical realization regarding the nature of existence, and the implications of this disappearance are as infinite as the void itself. The standard interpretation of gravity suggests a terrifying finality. Once matter traverses the horizon of events, the geometry of spacetime becomes so warped that all paths lead to the singularity. In this view, the information composing the star, its atoms, its quantum states, its unique signature in the tapestry of the universe, is annihilated. It is as if the universe were a grand library and the black hole were a furnace burning the pages of history. This perspective aligns with general relativity, where the singularity is a point of infinite density, a mathematical endpoint where the known laws of physics cease to function. If information is indeed lost, then the universe is not the stable record we once imagined. It would mean that physical processes are not strictly reversible, and that history can be permanently deleted from the cosmic database. This creates an unbridgeable rupture, as the destruction of information conflicts with the fundamental tenets of quantum mechanics, which demand that the past must be recoverable from the present. We are confronted with the possibility that the universe is essentially leaking, losing the precious details of its own evolution with every star that crosses into the dark. Such a total loss would imply that the universe is fundamentally incomplete, a system where the total count of variables can decrease, leaving behind a permanent, untraceable absence. However, the holographic principle offers a starkly different and more hopeful interpretation of this dark drama. It suggests that the information is not destroyed at all, but rather imprinted upon the two-dimensional surface of the event horizon. Much like the complex data of a three-dimensional object is encoded on a flat credit card strip, the entire history of the fallen star remains etched on the boundary of the black hole. This view posits that the horizon acts as a perfect memory, a storage device of universal proportions that keeps the star alive in a state of eternal encoding. By preserving this information on the surface, the universe maintains its integrity, ensuring that no physical state is ever truly erased from existence. If this holds true, then the singularity is not an endpoint of deletion, but a sophisticated transition of data. The information is not trapped inside the void, but held in staccato form on the threshold, a final testament to the matter that crossed over. This perspective forces us to view the event horizon not as a gateway to nothingness, but as a dense, complex shell of preserved history. The universe becomes a coherent system where every detail, every particle, and every collision is accounted for, forever safe from the crushing pressure of the singularity's core. Memory, in this framework, is the ultimate law of nature, triumphing even over the crushing pull of the most extreme gravitational giants. The clash between these two perspectives, the destructive singularity and the holographic memory, is what we call the information paradox of Hawking. It is not a mere technical disagreement, it is a fundamental crisis that reveals a missing link in our scientific language. To resolve it, we must bridge the gap between Einstein's gravity, which governs the macroscopic universe, and the quantum laws that govern the microscopic scale. This paradox suggests that our current understanding of the universe is like a book with half the pages written in a language we have yet to translate. Perhaps the solution lies in a new framework where spacetime is not a smooth, continuous fabric, but a quantum entity that allows for the preservation of information in ways we have not yet modeled. The fact that this conflict exists is perhaps the greatest indicator that we are on the verge of a deeper discovery. It hints at a reality where the black hole is not just a destroyer, but a processor, a component of the universe that rearranges information into a form we are only beginning to grasp. By forcing us to reconcile these two opposing truths, the paradox acts as a catalyst for the next great leap in science. It shows that the universe is not just matter and energy, but a vast, interwoven structure of information, a cosmic tapestry where even the most violent disappearances are governed by logical, quantifiable rules waiting to be decoded. What does it mean to inhabit a universe that guards its own history so fiercely? Whether matter is erased by the singularity or preserved by the holographic shell, the search for the answer defines the very purpose of our existence. We are the observers of this paradox, the beings tasked with peering into the void and asking where the truth lies. The study of black holes and the preservation of data is the ultimate test of our intellectual capacity. It forces us to look past the immediate darkness and perceive the underlying order. Perhaps the black hole is simply a challenge, an invitation to evolve our understanding of what reality is. As we continue to map the stars and calculate the nature of the event horizon, we are not just solving a riddle, we are documenting our own place in the grand narrative of existence. The memory of the star, whether floating on the horizon or scattered into the fundamental fabric of space-time, persists as long as we continue to ask. We remain the witnesses of this grand cosmic dialogue, forever tethered to the belief that in a universe as complex as ours, nothing of true value is ever truly lost. Even in the presence of the infinite dark, the desire to understand provides a flicker of clarity, a way to hold on to the past while we reach toward the future. The paradox is not an impasse, it is a signpost pointing us toward a truth that is, and will always be, worth the effort of discovery. The night sky is not a random collection of lights, but a map of possibilities filtered by our own perspective. We stand on a world perfectly bathed in sunlight, where the rhythm of days and seasons dictates the existence of everything we call life. This delicate dance around our star creates the comforting illusion that existence is inherently linked to daylight. Yet, this reliance on the sun creates a blind spot in how we measure the universe. We look for life as if it were a mirror of our own, scanning the horizons of distant solar systems for the familiar warmth of a sun-drenched surface. This quest for the habitable zone is the backbone of modern astronomy, a quest to find another home that mimics the conditions we already possess. But if we fixate only on the sun, we risk ignoring the possibility that the universe has developed other, quieter, and far more hidden ways to sustain the spark of biology in the darkness between stars. The traditional framework for finding life has always centered on the Goldilocks principle. A planet must be at just the right distance from its star to maintain surface liquid water. If it is too close, the atmosphere burns away or becomes a toxic high-pressure oven. If it is too far, the water freezes into a permanent, sterile block of ice. This habitability zone is a consequence of stellar energy, a direct product of the flux of light reaching a planetary surface. Our own solar system is the ultimate model for this, where the sun gives life the steady energy needed for photosynthesis and climate stability. This stellar reliance is the foundation upon which we evaluate exoplanets. Without the constant arrival of photons, the energy budget of a planet usually collapses. The surface temperature drops, the chemical cycles slow, and the possibility of complex evolution seems to freeze solid. It is a logical, verifiable, and measurable metric, but it assumes that sunlight is the only viable currency for life. By treating the habitable zone as the ultimate arbiter, we categorize most of the galaxy as a barren wasteland, defined solely by its distance from a sun. However, nature rarely confines itself to our convenient definitions. The habitable zone is a convention based entirely on surface conditions, ignoring the profound biological potential that exists beneath the frost. On worlds like the icy moons of our own solar system, liquid water exists far beyond the reach of stellar warmth. Here, heat is not a gift from the sky but a product of the planet itself. Radioactive decay in the rocky mantle and tidal flexing from gravitational interactions generate a persistent, internal energy supply. This internal heat can sustain global oceans for billions of years, sealed safely beneath kilometers of protective ice. These worlds are not rogue accidents, they are physical realities that challenge our reliance on the sun. If a frozen rogue planet can harbor a subterranean ocean, it bypasses the need for a host star entirely. In this view, the habitable zone is merely a thin layer of reality. The deep ocean floor, warmed by hydrothermal vents, represents an independent, dark, and resilient environment where life could thrive on chemical energy rather than solar radiation. This perspective shifts the entire paradigm, suggesting that the galaxy might be teeming with life in places we once deemed absolutely silent. Habitability is not a static ring around a star, but a spectrum of energy availability that defines the architecture of life. The reality of the universe is far more flexible than a simple distance measurement. While the surface of a starbound planet offers the most energy-efficient environment for complex life, the interior of a wandering world offers a secure, long-term sanctuary. We must broaden our scope to include both the brilliance of starlight and the smoldering embers of planetary interiors. A planet's ability to host life depends on its capacity to trap and utilize energy, regardless of whether that energy comes from a sun or from radioactive decay, tidal stretching, or chemical gradients in the crust. Hydrothermal vents, deep-sea crustal activity, and geothermal reservoirs are all legitimate power plants for biological evolution. By integrating these different sources of power into our understanding, we transition from a stellar-centric view to a planetary-centric one. This synthesis reveals that the galaxy is not a collection of suns with scattered ornaments, but a vast, interconnected ecosystem of energy-producing worlds, each with its own internal time clock and potential for chemistry to cross the threshold into life. We are realizing that our definition of home was far too narrow. By acknowledging that a rogue planet can sustain a secret sea while drifting through the silent, starless stretches of the Milky Way, we accept that the universe is not obligated to provide us with a sunrise to be alive. The cosmos is filled with hidden rooms, each potentially housing the machinery of existence in the dark. We have moved beyond the binary view of habitable or barren, arriving at a nuanced appreciation for how heat and chemistry interact over cosmic timescales. The next generation of telescopes, peering through the clouds of gas and the veil of distance, will search for the thermal signatures of these hidden oceans. We may find that the true census of life is written in the deep heat of cold worlds rather than the bright glints of stars. The universe has always been vast and strange, but our expanding vision ensures that we are no longer staring at a void. We are looking at a galaxy packed with hidden potential, a vast dark ocean of worlds where life waits, protected by ice and powered by the planet itself. The horizon of our knowledge is expanding, and it includes the quiet possibility that we are not the only ones who have learned how to hold on to heat in the cold expanse of space. There is a horizon in the sky that no telescope can pierce, a limit set not by optics, but by the very fabric of spacetime. We live in a bubble of information, an observable universe bounded by the time light has had to travel since the dawn of everything. Beyond this edge lies a reality that exists, but one that is permanently cut off from us. Every second, the horizon shifts, and the observable volume of our reality undergoes a silent transformation. We are situated observers in a cosmos that is expanding, creating a gap that no physical signal can ever traverse. This is not a temporary limitation of our instruments, but a structural reality of the universe itself. We must confront the realization that the cosmos we catalogue today is merely a fragment of an infinite expanse that remains fundamentally unreachable, a silent void where galaxies drift away into eternal isolation, forever beyond our reach. The pursuit of knowledge is driven by the conviction that our horizon is merely a technical barrier that time and technology will overcome. As we look into the deep past, the James Webb Space Telescope and its successors reveal structures from the infant universe, pushing the boundaries of what we identify as the observable cosmos. The prospect remains that with more powerful instruments, we might detect signals from regions currently obscured by dust or distance, theoretically expanding our map of the universe across trillions of years. If the geometry of the universe allows for stable configurations, then future civilizations could potentially chart vast swaths of the cosmos, mapping the intricate filaments and superclusters that currently lie hidden. This optimistic view suggests that we are at the beginning of an era of unprecedented exploration, where every advancement in light detection acts as a beacon, turning the unknown into a searchable, catalogued reality, eventually bridging the gap between isolated clusters and building a coherent, unified portrait of the entire cosmic web. However, this vision of an ever-expanding map fails to account for the harsh reality of dark energy and the acceleration of space expansion. The universe is not merely growing, it is tearing itself apart at an accelerating rate. This cosmological event horizon is an invisible barrier that defines the ultimate limit of present and future contact. Galaxies are currently crossing this threshold, disappearing from our future reach as the space between us grows faster than the speed of light. In the cold calculus of the distant future, the lake of the observable universe will gradually evaporate. Stars will exhaust their fuel, and those galaxies not gravitationally bound to our local group will be swept away into a dark, inaccessible abyss. We are witnessing the slow death of the cosmic narrative, where the vast, rich complexity of trillions of galaxies is being silenced by the expansion of space itself. The future is not one of exploration, but of inevitable, profound solitude. The contradiction between our desire to know and the structural limitations imposed by dark energy reveals the unique nature of our existence. We are trapped in a rare window of opportunity, a specific cosmological epoch where the echoes of the Big Bang, the cosmic microwave background, and the distribution of distant galaxies are still accessible. This is a fleeting moment in the history of a cosmos that will eventually hide its own past. Our capability to reconstruct the history of the universe is a privilege that observers in the far future will not possess, as the evidence will have long since crossed the cosmological event horizon. Despite the inevitability of this growing isolation, our ability to document and understand this process allows us to grasp the reality of the whole. We are the mechanism by which the universe becomes aware of its own limits, and in doing so, we define our own place as the witnesses of a disappearing cosmic archive. We are spectators in a theater where the stage is gradually being removed, yet we have arrived just in time to read the play before the final act. The study of the observable universe is not a futile exercise in cataloguing a shrinking bubble, it is a desperate, beautiful attempt to preserve the identity of the cosmos before the darkness becomes absolute. The fact that the universe remains real beyond our reach does not diminish our discovery of the laws that govern it, nor does the inevitable isolation negate the importance of the connections we have measured. As we gaze into the past, we are reading the correspondence of stars that have already faded and galaxies that are already lost to the horizon. We are the universe finally recognizing its own boundaries, and in the quiet of this knowledge, we find that to witness the cosmos, even for a brief moment, is enough to justify the immense, lonely journey of existence through a space that is eternally expanding away from our light. The solar system appears as a clockwork arrangement of orbits, a predictable cosmic dance that suggests a slow and peaceful birth. When you look at the planets revolving around the Sun, you see stability, order, and the quiet outcome of gravity acting over billions of years. It is tempting to imagine our neighborhood starting in a vacuum, a simple collapse of a cold molecular cloud that slowly condensed into the Sun and its planets. This peaceful vision offers a sense of comfort, a perspective where our origins are rooted in the natural, steady laws of physics. Yet, this image of an isolated, serene beginning hides a much more dramatic reality. If the solar system was merely a quiet byproduct of a collapsing cloud, how do we account for the chaotic architecture of the outer planets or the specific chemical signatures trapped in ancient meteorites? Perhaps the history of our birth is not a lullaby, but a violent wake-up call delivered by the galaxy itself. Beneath the stillness of our orbits lies a secret waiting to be told. The standard narrative of solar system formation relies on the gravitational collapse of a giant molecular cloud, a process occurring in the solitude of the interstellar medium. According to this view, gravity pulls the gas and dust together, naturally increasing the density until the center becomes hot enough for nuclear fusion. As the Sun ignites, the remaining material forms a flat, rotating disk where planets grow through steady accretion. In this scenario, the solar system is the result of internal processes, a self-contained environment that does not require external intervention to trigger the birth of a star. This perspective implies that systems like ours are common, emerging wherever enough gas gathers in the darkness. It paints a picture of isolation, where the Sun and its planets grew in a sheltered nursery, free from the direct influence of the violent cosmic events that frequently tear apart other regions of the galaxy. It is a story of natural, unhurried progression, where gravity alone directs the formation of a solar system from start to finish. Gravity acting in isolation may not be enough to explain the specific triggers that jumpstart star formation. Evidence from the Milky Way reveals that the galaxy is a place of constant agitation, defined by collisions and gravitational tides that compress gas into new structures. When dwarf galaxies like Sagittarius interact with the Milky Way, they send ripples through the interstellar medium, acting like cosmic pistons that force dense clouds to collapse faster than they would on their own. Studies show that star formation in our galaxy was once slowing down until an external event accelerated the process nearly 5 billion years ago. This timing matches the arrival of the solar system, suggesting that our birth was not an accident of nature, but the direct result of a shock wave. Instead of a serene nursery, our origin may have been a high-pressure zone, forged in the wake of a galactic collision that packed molecules together with enough force to ignite the Sun and prevent the cloud from simply drifting apart. The reality of our origin likely lies in the middle of these two extremes, combining natural gravitational potential with a decisive external trigger. While the molecular cloud had the inherent capacity to collapse, it may have hovered in a state of equilibrium, waiting for a catalyst to tip the scale. The collision with the Sagittarius dwarf galaxy acted as that necessary disturbance, creating the density needed to transform a diffuse cloud into a stable, massive core. This violent compression provided the material density required to build giant planets and sustain the Sun's early development, explaining why our system possesses the specific chemical fingerprints we observe today. Without this interaction, the cloud might have remained a thin structure, eventually dissipating into the void. Thus, the solar system is not merely the product of gravity, but a masterpiece created by a unique encounter. We exist because the galaxy collided with itself at the exact right moment to turn a dormant cloud into the cradle of life. The birth of the Sun and its planets is a testament to the fact that isolation is an illusion. We are the survivors of a cosmic negotiation, where the slow force of gravity met the explosive pressure of a galactic ripple. By looking at the scars left on the Milky Way, we can reconstruct the moment our home began to take shape, emerging from the collision of gas clouds and the sheer momentum of a passing dwarf galaxy. This discovery changes our understanding of our place in the cosmos. We are not just dwellers of a stable system, but the beneficiaries of a chaotic and interconnected universe. Every orbit we track is a link to that original, sudden ignition. As we continue to map the motions of stars and the ripples of gas across our galaxy, we find that our history is written in the movements of the entire Milky Way. The solar system is not a quiet bubble, but a dynamic participant in a larger, ever-changing drama that defines the life cycle of every star. The night sky is a silent archive of the past. When you look up, the light hitting your eyes is not the universe as it exists at this exact moment, but a delayed message from billions of years ago. We are located observers, trapped within a bubble of information defined by the finite speed of light and the age of the cosmos. This observable universe, with its 93 billion light-year diameter, feels like an infinite expanse to our fragile senses. Yet, we are situated in a tiny corner of a reality that is vast, indifferent, and mostly unreachable. Every star is a beacon of time, telling a story that was written long before we emerged from the cosmic dust. We stare into this void, asking why we are here to witness it. We are curious, driven by a persistent need to map the invisible. But does the universe care that we are watching? Or are we merely a fleeting accident in a cosmic play that does not need an audience? We are about to uncover why our very existence might be the most strange phenomenon of all. Consider the scale of the Milky Way, with its 400 billion stars and its cold, dark, indifferent expanse. We occupy a small rock orbiting a standard star in a quiet arm of a spiral galaxy. Statistically, our existence is a rounding error, a brief flicker of biology occurring in a universe that has existed for 13.8 billion years without us. The cosmos is filled with neutron stars nearing collapse and black holes devouring light in complete silence. There is no evidence that the universe was designed for our perception or that its laws shift to accommodate our gaze. Physics continues to operate whether we understand it or not. Dark energy drives the expansion of space, pushing distant galaxies beyond our event horizon, erasing the records of existence without a single regret. We are not the protagonists of this narrative. We are a biological byproduct of the same stellar alchemy that forged the elements in the core of dead suns. We are carbon and water, temporarily organized into patterns that allow us to think, only to eventually dissolve back into the stardust from which we came. To suggest that human consciousness is central to this physical reality is a form of vanity that ignores the cold, harsh, and mathematical nature of the vast cosmos. However, look at the geometry of our reality. The paradox of the observer is that the universe only acquires definable properties when a measurement occurs. Before the first conscious mind looked up, the cosmos was a sea of probability, a wave function of infinite possibilities that had not collapsed into a single, observable history. In this view, consciousness is not an accident, but a fundamental requirement for the reality we describe. Without an observer to measure distance, time, and the expansion of space, the concept of a universe becomes empty of meaning. We are the sensors of the cosmos. Our telescopes and our minds act as the eyes of the universe, focusing its scattered, chaotic nature into a coherent picture. We do not just inhabit the cosmos, we structure it. The very fact that we can calculate the age of the Big Bang, that we can trace the motion of asteroids with Gaia's precision, and that we can describe the curvature of spacetime, suggests that the universe has an intrinsic tendency to manifest order through consciousness. We are not just inside the room, we are the ones who turn on the light. The universe, in its rawest state, requires a mind to translate its physical forces into the laws of nature that we recognize as reality. The resolution of this tension lies in the idea that we are the medium through which the universe experiences its own existence. We are not irrelevant, but we are also not masters of the stage. We are the universe folded back upon itself, a complex arrangement of atoms that has achieved the ability to feel, to measure, and to ponder its own vastness. Think of a planet without a sun, drifting through the dark lanes of the Milky Way. It has its own gravity, its own heat, and its own deep, hidden oceans, but it possesses no way to know itself. It is a world in the dark, existing without awareness. Consciousness is what turns that darkness into a domain of knowledge. By measuring the limits of our observable bubble, by identifying the event horizon that separates the reachable from the permanent unknown, we are performing a cosmic task. We are drawing the map of existence. We are the way the cosmos measures its own diameter. Our consciousness is the instrument that transforms simple matter into something that recognizes its origin in the Big Bang. We are the synthesis of the indifferent physical forces and the meaningful experience of reality. We exist to be the witnesses that the vast void would otherwise lack, turning the cold calculations of thermodynamics into the beauty of an observed, understood, and meaningful home. We are travelers on a planet that is merely one among trillions in a galaxy that is merely one among billions in a universe that might be infinite. This sense of smallness, while disturbing, is exactly what gives us our perspective. We are observers of a horizon that is silently receding, a bubble that is slowly isolating us from the rest of the cosmos. We are here during a privileged moment, the only time in the history of the universe when the evidence of its beginning is still reachable. We were meant to observe, to record, and to understand, before the dark energy of an accelerating expansion pushes the evidence beyond our horizon. Our consciousness is a candle lit in a vast, dark cathedral. The candle does not make the cathedral larger, but it makes the space understandable. We do not need to be the center to be significant. We only need to look. As we move forward into the future of our tiny bubble, let us remember that the universe is larger than any possible confirmation. We are the observers who gave it a name, a history, and a voice. The quiet journey through the stars is our journey, and the meaning we find in the dark is the meaning we bring with us.